Yeah, my name is Sergey Tsirkan. I'm a research material scientist at Avalanche, and I head up the plasma-facing component development, materials discovery, and extreme environment materials. So high entropy alloys are these sort of really cool sounding materials, but really if we just take a step back and compare traditional materials, a traditional material is, let's say, tungsten, or aluminum, or copper, or nickel, and has a very definite crystalline structure, has a lot of grains, so many little different parts, but it's the same material within each little part of the material. When you take a high entropy alloy, you actually mix 2, 3, 4, 5, 6, maybe more elements together, and it sort of becomes this like disordered soup of materials, of elements rather. But the difference is that it still has a crystal structure, it's just made up of different little parts. So it's like a flavorful alloy with a defined crystal structure. So this is what we call high entropy, because there is entropy, meaning there's an inherent disorder in the chemical structure, maybe not in the crystal structure, but there's a chemical disorder there's an inherent disorder in the elemental structure of the material. Materials in general, especially for fusion systems, are very difficult to solve, because if we just zoom out and we look at where they go, there's many different concepts. So there is, we have tokamaks, we have stellarators, FRCs, Z-pinch devices, we have compact fusion, us. And you look at the scale and the form factor of a fusion device, they will require different materials. So for example, what an FRC will use doesn't mean that something we will use or a tokamak will use. And the problem is further complicated by the fact that you have things like corrosive environments. Some devices may have more oxygen than others. Some may have more heat aging than others, right? Some may have temperature swings far faster or far greater for a sustained amount of time than others, right? So one material, the problem is more further complicated by the fact that you don't actually need to solve 1 or 2 or 3 materials. You maybe need to create 5, 10, 20 materials that solve various ranges of problems, right? So this is why it's difficult to do that on a timeline that we actually want to do that, because we've been doing this kind of research for decades, and we don't technically have a fusion material that everybody agrees on. So it's a difficult problem because we know it hasn't been solved for decades, but we also know that the energy is high that it needs to withstand from neutrons. We know that the energy from the impact from alpha particles, the effects from alpha particles are very hard to mitigate. So there's a lot of factors that are all intertwined, and it's really a synergistic kind of soup of problems that you end up having, and it's just very difficult to solve all of that for one single fusion material, or 5. Neutrons cause, so there's going to be 2 types of damage mainly for fusion materials. You're going to have a neutron ripping through the material, and because it has no electrical charge, it doesn't really interact strongly with the lattice of the material. What that's going to cause is that's going to cause physical damage. So something called DPA, displacement per atom. So it means that the more neutrons, the more flux of neutrons, so the higher rate of neutrons you hit your material with, you're going to cause much more atomic displacement damage. That's going to cause a few things. Physical embrittlement, void swelling, meaning you're going to create voids that are kind of like swell up your material, and you're going to cause something called transmutation effects. That one's a big one, because transmutation is where a material captures a neutron and makes a different isotope of something. For example, you can create helium inside of your material, helium production. That's a problem because helium will agglomerate and bubble up. So you have something called helium bubbling in your materials. So and then there's the alpha particles, which generally, it's a helium itself, right? It's a stripped down helium atom. So you have those 2 types of damage, and that's really the main problems that we're trying to solve. High entropy alloys could be the solution to many problems because you can tailor their properties to such a high degree. So for example, you can, because it's 5, 6, or 7, or 3 or 4 elements mixed together, you can actually kind of see which properties you want to tune for which purpose. For example, you want high temperature resistance, maybe you go with some high temperature material. You want high impact resistance, meaning maybe low sputtering rate, maybe you go with tungsten, right? Perhaps you want something that doesn't activate much, so you have to look at the activation profile of the material. There's a lot of different things you can tune about these materials, so it gives you a lot of flexibility. High entropy alloys have really only been around for the last 20 years. We've always known that the more materials you mix together, meaning the more elements you mix, things become brittle generally. So they become brittle, which is why high entropy alloys weren't really thought of as great performing materials or choices for these systems. And just recently, there has been great work by one of the founding fathers of the HEA field, high entropy alloy field, Brian Cantor out of Oxford University. he kind of revolutionized that whole entire field by showing Cantor alloys that have shown improved properties. So, and that's how the field got kicked off. Yeah, so it's kind of interesting because sorry, it's kind of interesting because as a fusion community, we've single-handedly almost focused on plasma physics, and we should, right? Because that's really what matters for producing power. The problem is, if you don't have a reactor made out of the material that can withstand fusion, you don't have a reactor. Like, you don't have one that lasts, one that produces power, one that doesn't need to be, serviced every month, for example, or every few weeks. So to have a working reactor, you have to solve the materials problem. That's a paramount part of the problem. No material, no fusion. So that really is what material scientists have been kind of trying to bring up in the past 10 years, 15 years, saying we need to focus more on materials, because as we're kind of advancing and running away with the plasma physics problem, we're kind of lagging behind a little bit with material solutions. And that will take just as much time and effort as the plasma physics problem. So for the community in general and for our concept specifically, the reason what I do really matters is because of the form factor of Avalanche, right? Small compact fusion. We get to explore a lot of novel ideas for material solutions, whereas maybe a big concept won't have that flexibility because of supply chain issues, cost, form factor, manufacturability. This gives us a unique advantage to where we can say we can take a novel material, a high entropy alloy, we can synthesize it in a smaller form factor, so it's not going to cost as much as for a big guy, and so I get to contribute in various different ways and try out various different things and really do materials engineering and bring the company solutions with a few different flavors. We can say as a material science team, if we need more DPA damage resistance and sputtering, we're going to maybe give you a tungsten-based alloy. If it's a production, let's say a neutron generator versus then a power production device, we can give you a different material, right? So a lot of flexibility, and I believe it's going to go into work much sooner than a bigger concept because it's a smaller concept. Yeah, so as it turns out, high entropy alloys have dual use applications. So for example, when it comes to Avalanche, we're creating high entropy alloys for fusion. It just so happens we also have a Air Force project where we create high entropy alloys for the Air Force. As it turns out that if you can create a good material in fusion, high entropy alloy for fusion, it'll probably be good enough for a lot of different extreme environments. Part of the reason is because they're highly tunable properties, because you're mixing a lot of things together, so you can really pick and choose what you want to lean into. For example, high temperature applications, you may want to go the ceramic route a little bit. Sputtering resistance, you may want to go the tungsten route a little bit. So you really can pick and choose which properties you want to lean into and then tailor those. So it's a highly tunable system, and it gives you a lot of range of performance, whether you want oxidation resistance, whether you want sputtering resistance, whether you want a high temperature resistance.